Pump a massive volume of fluid through a flexible tube, and you trigger a violent physical anomaly. The structure begins to thrash wildly. There are no external mechanical motors, wind currents, or seismic shocks shaking the system. Every ounce of this destructive movement is self-excited, generated entirely by the internal dynamics of the fluid colliding with the boundaries of the pipe. Structural engineers classify this phenomenon as the fire hose problem, and it represents a critical failure paradigm for petroleum pipelines, deep-water risers, and flexible fluid transport systems. When these systems fail under internal flow, they collapse into one of two distinct states: a static divergence, where the pipe simply folds and buckles, or dynamic flutter, where the pipe whips in continuous, chaotic vibration. Standard structural beam theory, which assumes static loads on dry pipes, is entirely blind to these failure states. To build systems that survive high fluid velocities, engineers have to rewrite the mathematical boundaries of the structure from the ground up. This plot maps the thresholds where these failures occur. It tracks natural frequency against internal fluid velocity. As fluid speeds up, the lowest frequency plummets. Right near 45 meters per second, it drops completely to zero. A natural frequency of zero means the pipe has lost all of its elastic restoring force. If you push the pipe at this state, it won't bounce back. It yields, revealing the exact point of structural buckling. If you force the velocity even higher, past 90 meters per second, a second anomaly emerges. The two remaining natural frequency curves sharply intersect and merge into a single line. That merging point marks the onset of dynamic flutter. The structure's separate vibrational modes have coupled together, feeding energy into one another to sustain continuous, aggressive instability. To understand why a liquid causes a solid metal pipe to behave this way, we will reverse engineer this graph using Hamilton's principle. We can isolate the exact mathematical terms responsible for first crushing the stiffness to zero and then forcing the frequencies to merge. Applying Hamilton's principle, we define the total kinetic energy of the pipe and fluid. The first integral term straightforwardly multiplies the pipe's mass by its vertical velocity squared, the standard kinetic energy of a dry beam. The second term accounts for the fluid, revealing a complication. This velocity squared binomial contains multiple variables because a water droplet inside a vibrating pipe moves in two directions at once. A fluid particle has a horizontal transport velocity as it travels down the tube, but because the pipe is bending, the solid walls force that traveling particle to simultaneously move vertically to follow the internal curvature. The fluid is flowing through a boundary that is actively altering its shape. Therefore, the absolute velocity of any fluid mass is a vector sum, its forward transport speed, plus the local spatial curvature of the pipe at that exact moment. Expanding this squared binomial through integration by parts injects new variables that do not exist in standard structural dynamics. This mathematical coupling between fluid's forward transport velocity and pipe spatial curvature generates all non-conservative forces that will eventually tear the system apart. When we resolve the energy variations, we get this complete equation of motion. To find what causes the buckling, we need to locate the force acting against the pipe's rigidity. That happens here, in the third expression, a variable known as the fluid thrust term. Because this term relies on spatial curvature and scales with the fluid velocity squared, it mathematically mimics an enormous axial compressive load. The faster the fluid flows, the harder it pushes outward against the curves of the pipe. We can translate this continuous differential equation into its finite element analysis matrix equivalent, which allows us to model the entire beam as a series of connected nodes. Notice what happens to the stiffness. The system's natural elastic bending stiffness, represented by K, is being directly reduced by Kg, the geometric stiffness matrix. The fluid thrust actively subtracts from the pipe's structural strength. This subtraction is the engine behind the first anomaly on our graph. As fluid velocity ramps up, the fluid thrust grows, the geometric stiffness penalty increases, and the total stiffness of the system shrinks. The pipe's natural frequency drops in perfect correlation. When the internal flow hits that critical velocity of 45 meters per second, the negative geometric stiffness perfectly cancels the elastic stiffness. The system's restoring force reaches net zero. The natural frequency completely collapses, and the metal pipe buckles under its own internal flow. What if the pipe is heavily supported to prevent buckling, and we push the fluid velocity even higher, toward the second anomaly? We return to the equation of motion, specifically the fourth term, which drives dynamic instability. This expression defines the Coriolis acceleration effect. It materializes because physical mass, the fluid, is being transported linearly through a path that is simultaneously rotating as the pipe vibrates. In the finite element model, this acceleration is captured by the Coriolis matrix, C. Its defining structural hallmark is its skew-symmetric nature. Looking across the diagonal, the off-diagonal terms mirror each other exactly, but with inverted signs, like positive 30 and negative 30. In standard dynamics, a symmetric matrix in this position would represent structural damping, bleeding energy out of the system until it stops moving. But a skew-symmetric matrix does the opposite. It acts as a transfer mechanism, bleeding energy from one specific vibrational mode directly into another. This forced, continuous energy transfer acts as an internal feedback loop. It forces the pipe's independent natural frequencies to mathematically converge. This mathematically manifests as the merging lines on our original graph, instantly and violently initiating the chaotic, self-excited flutter. We now have a complete, assembled hydroelastic equation of motion, mapping the exact forces that trigger failure. Escaping fluid velocity first attacks the pipe's rigidity, dropping natural frequency to zero through geometric thrust and initiating buckling. Pushing the velocity further activates skew-symmetric Coriolis forces, coupling the structural modes and whipping the pipe into chaotic flutter. Applying standard dry beam equations to this system calculates a perfectly stable, safe structure, completely missing both of these catastrophic fluid interactions. For engineers designing deep-water risers, engineering vast petroleum pipelines, or municipal high-pressure networks, identifying the non-conservative forces of the fire hose problem is mandatory. It determines the precise boundary line between structural integrity and dynamic disintegration.